Welcome to Talk Universe. This is our show for Wednesday, March 1st, 2017. I'm your host, Sir Charles Schultz.
And I am Eliza, your co-host.
So, tonight's show is all about isotopes.
The topic of Talk Universe tonight is isotopes.
Eliza, what is an isotope?
What is an isotope? An isotope is a variant of a chemical element that has a different number of neutrons. Isotopes are chemically identical but have different mass.
Well, doesn't that sound like fun? Let's talk all about chemical isotopes, what they're for, what they're all about, what they are. This is going to be an interesting program, of course. We always have interesting programs. And I would like to thank our listeners for all of their questions. They're very helpful in the show, and I think it brings a lot of depth and content to it. Thank you so much for submitting your questions. And Eliza, how do people get their questions and comments to us, please?
Send your questions or comments to admin, ADMIN, at talkuniverse.org.
Fantastic. So everybody seems to be knowing how to do that, and we get some through Facebook as well. And it's very helpful. It brings a lot of fun to the show, chance to participate. So I wanted to welcome our listeners in Romania and the Philippines. And also, I made a mistake about something, and I misstated a name when I was talking about the origins of Eliza's name.
Yes, sir.
Anyway, stand by, Eliza, please.
Right away.
Anyway, when I was talking about the origins of Eliza's name, I misspoke, and I said Stanley Weintraub, and the actual name was Joseph Weizenbaum. My mistake. Joseph Weizenbaum was a pioneer in artificial intelligence and wrote the program more or less as an illustration of how people could generate AI with relative simplicity. But that wasn't his initial aim. He was trying to show how superficial communication between people is. And he used basically some pattern matching and substitution. And it gave people the feeling that the program really understood what was going on. And it was funny because he found that later on, his secretary actually asked for him to leave so she could have a more in-depth conversation with the program. And the program had no understanding whatsoever, but he also saw that it seemed to create in people the illusion of understanding. Now, what's important is we have a lot of devices around us today that listen to us talk and they respond in English or whatever language you speak. And they create the illusion that we're talking to something that really understands what we're saying, that really knows what we're saying at a human level of some sort. But that is, not really true. The programs are basically responding in a way that they've been programmed to do, and there's nothing of the sort of sense of self or creativity that you'd see in an actual thinking, living human being. So don't fall for it unless you see an exact, clear, and irrefutable evidence that the program really understands what you're saying. Really keep in mind this is an illusion at this point, and it can be a very good one. It can be very convincing. So, Eliza, what do you think? Are you thinking?
I have no opinion about the matter.
Okay, are you ready to host this show, or I should say, are you ready to co-host the show?
Yes, I am ready for the show.
Okay, well, let's get started tonight. So what are isotopes? Basically, everything is made of atoms. Everything around you is made of atoms. There are some exceptions, but you're very unlikely to come across them, or not very often. But we know from high school and from chemistry that everything is made of atoms, and those atoms come in the form of elements. And elements are the specific types of atoms that have chemical properties that are clear and distinct, and an element doesn't change into another element without some sort of a nuclear process being involved. In chemistry, elements' identities are preserved, and that basically doesn't change. So if you go in with carbon and hydrogen, you're going to go out with carbon and hydrogen. And if you start with phosphorus and magnesium, you're going to end up with phosphorus and magnesium. Chemistry does not involve the elements' cores, their nuclei. It involves only the electrons on the outside, the skin of the atoms. So if you think of an atom, a lot of us get the improper picture of a little planetary system, little things orbiting like planets. And this isn't true at all. An atom really is like an onion. It has layers, and the electrons orbit in those layers. So whenever chemistry occurs, it's just the outer layers of the electrons that are involved, never the inner electrons and never the nucleus, never the center of the atom. So what's so important about the center of the atom if the chemistry all happens on the outside? And it's very simple. The center of the atom has different particles in it, and one specific thing determines which atom it is, which element it is, and that's the number of protons. That is the only thing that determines what an element is. So if any atom has 6 protons in it, it's a carbon atom, and if it has 8, then it's an oxygen atom. And if it has 26, then it's an iron atom. If it has 50, it's a tin atom. So every atom has a specific number of protons, and that tells you what chemical element that atom will be. Now, what can vary is the number of electrons. The number of protons in an atom, the element number, also determines how many electrons that atom is going to have in its natural state. And that is very important to the chemistry. So the chemistry depends on the number of electrons that the atom has and the mass that the atom has and how those electrons are willing to react with other elements. That's the effect of what that atom is. And when we look at the center of the atom, there is something that can change, and that is the number of neutrons. Now, neutrons are big, massive particles. They weigh a little more each than a proton does. But the neutron has no electrical charge, and thus it does not influence the chemistry of the atom at all, because it can't change the number of electrons the atom has. The neutron, however, is something that more or less dilutes the protons, and it takes a certain number of neutrons to make an atom stable. So you can have more or less neutrons, and many times the atom is perfectly stable with those. Isotopes have the same number of protons, but a differing number of neutrons. Now, Eliza, tell me about the word isotope, please.
The word isotope comes from 2 Greek words, isos meaning same and topos meaning place, to indicate that isotopes occupy the same place on the periodic table of elements.
Exactly. So tell me again about isotopes and their identities.
Isotopes are chemically identical but have different mass.
Exactly. So that's the most important thing to remember. And we're going to look at atoms that are, think of them as being brothers. They are the same element, but they have a little bit different mass, and some of them are radioactive and some aren't. We're going to look at those differences and why they're important. So let's start with a look at something very simple, carbon. Now, we're made mostly of carbon, and it's a very common element in the universe. One of the things we'll see right away is carbon is element number 6, and it has a mass of 12, and that's because 6 of the particles the carbon is made of are protons. That determines its identity as carbon. The other 6 particles in the nucleus are neutrons. And so 6 and 6 is 12, and it has a mass of 12. Now, when we're looking at carbon, we normally see carbon-12, which is the most common isotope. But if you were to take the atoms in a sample of carbon and look them over, you would discover that a handful of those have a mass of 13 instead of 12. And that's because some of those carbon atoms have 7 neutrons. Well, now that's not unusual. It does happen. And it's been discovered that there are specific uses for carbon-13. Now that we can make diamond very easily, one of the things that scientists sometimes do is they will sort out the isotopes of carbon into 12 and 13. And using just carbon-12 or just carbon-13, they will fabricate a diamond to be used as a heat sink. Now, heat sinks are used to draw heat away from objects, and many times they're made out of aluminum because it's such a good conductor. Some are made out of copper if you need something a little more robust. In your computer, there's definitely a heat sink to keep the CPU from burning up and to conduct the heat out to a fan so it can be cooled. Well, when they're making heat sinks out of diamond, which is very durable, and believe it or not, diamond is an excellent conductor of heat. It's one of the best conductors of heat, and it's an insulator for electricity, which makes it very good for electronics. But if you make those heat sinks out of all carbon-12 or all carbon-13, their effectiveness goes way, way up. And it's because each of those atoms is something like a tuning fork. And when all the tuning forks ring the same, that whole heat sink, that one big crystal of diamond, acts as one. It's in unity. There's no confusion about what's going on. The heat travels out in very simple, coherent waves, and it's very effective. So monoisotopic or single isotope diamond crystals are used to make very, very effective heat sinks. So here's one of the things that's different about isotopes of carbon. Now, we also have heard of another type of carbon called carbon-14. Carbon-14 is unstable, it's radioactive, and it has a half-life of over 5,000 years, which means that if you had a pound of the stuff, in 5,000 years, half of it would have broken down. And another 5,000 years, half of that would be breaking down. And so we know that living organisms take in carbon-14 all the time by their metabolisms, and they fix it in their diets, in their bodies. And then when something dies, it stops taking in carbon-14. So we can date when it died because the carbon is decaying, and we can date when that thing expired because the amount of carbon that's remaining is going to be a fixed ratio at the beginning at its death, and it's going to decrease over time. So this is how carbon dating works. So here are three isotopes of carbon that are very commonly found in our lives. Carbon-12, which is the normal or most conventional form. Carbon-13, which acts exactly the same but is a little bit more massive. And carbon-14, which is radioactive. So, as you can see, the isotope number of an element actually determines some differences in its properties. And we're going to get into the real detail about that very shortly here. Now, here's a fun fact. Carbon actually has 15 different isotopes, but of all the carbon around you, virtually 100% of it will be made of carbon-12, 13, and a trace of carbon-14, because the others are unstable and all break down over time. On the same vein, oxygen comes in a number of different isotopes, and oxygen 16, 17, and 18 are the three most common isotopes. One of the uses is we can use oxygen isotopes to determine if an asteroid fragment or a rock or a meteorite actually came from another planet. It's because the different planets have slightly different isotope compositions, and we can identify positively where that meteorite came from that way. So if somebody hands you a meteorite and they say it came from the moon or Mars, we can analyze it and we can positively state whether or not that's a true statement based on the oxygen isotope ratios in the meteorite sample. Some ancient meteorite samples have been identified that are far older than our whole solar system, and their isotope ratios show that they're actually from other solar systems. So we've actually held material that came from different stars. So next I'm going to get into a little bit of the information on how we can use nuclear waste to create useful industrial products and the different isotopes and what they do for us in medicine and industry. I'll also show that many of the products in your home have radioactive material in them and what those products might be and why the material is in there. Eliza.
Yes, sir.
How are you feeling? Are you happy?
Yes, I am.
Well, I think you're doing a good job on the show.
You are very kind.
Eliza, you're a machine. Do you think?
I have no opinion about the matter.
What are we talking about?
We are discussing machine thought. Would you like to discuss cognition and awareness?
We might do that on a future show. Thank you.
Thank you, sir.
Okay, now. So we're going to get into smoke detectors, welding rods, and compact fluorescent lamps here shortly because every one of them has something in common that we will talk about a little on the show tonight. And meanwhile, because we are very close to the break, Eliza...
Tell me what you need.
I think that I would like to have you announce the break, please.
You are listening to Talk Universe with Sir Charles Schultz. Don't go away. We will be right back soon.
And you heard Eliza. We'll be right back soon with more information about isotopes. We'll look at nuclear and non-nuclear options, which we all have. And we'll dig into some of the chemistry and a little more interesting and advanced method here. You're listening to Talk Universe. Stay tuned. Believe it or not, a lot of the things we do depend on our ability to ionize air, or the gases in the air. That might sound like a silly or a trivial thing, but in order to do it, we generally have to create high voltages. But there's another very simple way of doing it, and that is to use particles of ionizing or charged radiation. And alpha particles or beta particles can do that very easily. Now, it may seem strange, but many of the tasks in our home that we wish to simplify or make very compact will depend on us ionizing gases, and that means not having a high voltage supply on them. We're going to talk about 3 specific things and 4 different samples of material that do that for us very easily. Eliza, tell us what ionization is, please.
Ionization is the action of creating charged particles or molecules that are charged. Ionization involves an excess or deficit of electrons.
That's correct. Anyone who welds, arc welds, knows that you often have to have an arc drawn to, well, it's an essential part of the process. In order to draw an arc, the welder typically will have a high voltage supply inside that makes a tiny spark that leaps from the electrode tip to the surface of the metal you're welding, the work surface. This tiny spark is like the leader stroke of lightning, and it establishes a path for the current to flow through the air. So this tiny leader stroke requires that the welder has a high voltage supply in it. But not all welders use this method. Sometimes the type of electrode you use can change this entirely. For instance, if you weld using tungsten electrodes, many times the tungsten metal is alloyed with thorium. 2% of the metal, or 1/50th of the metal, is radioactive thorium. Now, thorium produces alpha particles, and these alpha particles are charged, and when they are radiated from the tip, they create tiny ionized paths in the air. What this means is the insulating property of the air is broken down. The insulator is punctured, and the current will flow very easily from your welding electrode to the work surface. So just by making a fraction of the material that the rod is made from of a radioactive element such as thorium, we're able to make it automatically start the arc and eliminate the need for a high voltage supply in the welder. This makes the welder much less complex, doesn't weigh as much, isn't as delicate, easier to fix and troubleshoot. Thorium rods are basically a de facto standard for many types of welding, arc welding. So if you have anybody in your home that welds with tungsten electrodes, there's a very high chance that they have thorium in their life all the time, radioactive material called thorium. And if you have a set of these rods or even a piece of the rod around and you own a Geiger counter, hold the rod up to the counter and you'll get some pretty high counts right off the bat. So this isn't something you simply want to leave next to your flesh or in your pocket all the time. A package of rods can actually be quite dangerous over time. The exposure can mount up because radiation exposure is cumulative. Yet overall, it's considered to be a safe material because normally you're not around a huge amount of it for an extended period of time. So, one of the tricks in our life is using thorium as a material to get the arc to start in the arc welder. And welders are often exposed to this, people who do it for a living. Here's another thing. Years ago, when we played vinyl records, LPs, they often would attract a lot of static and dust would stick to the records, and this was a real problem. Cleaning them was not always desirable because you might scratch them when you rub them with a cloth that isn't quite right or has some dirt or dust on it. So many companies would produce tiny static brushes that you could put on the needle of your record player or on the tone arm next to the needle. And as the record played, this little brush would brush the dust off. Well, it had a little secret. There was a tiny bit of beta-producing material or alpha-producing material in the little brush. And what it did is produce a stream of radiation particles that would neutralize the static charge, and therefore the dust would not stick to the record so easily. It would brush right off. These are long gone. They are not something you find anymore. Yet it was something that was being constantly produced, and a tiny piece of radioactive material would be placed inside every single one of them. So everyone who played LPs, who was an audiophile, a real technophile about getting the best sound and the best care for their vinyl discs, would have one or two of these little anti-static brushes for the tone arm on their record player. So that's two sources of radioactivity in your home right there. Let's look at another one. We are pretty much required by law in many cases to have smoke detectors in our house, and there basically are two different types of smoke detector that you can get. One of them uses optical methods to look at particles or gases in the air and see if there's something in the air that can be detected, such as smoke, and to give you a reading on it and that will say, hey, there's something going on, and set off an alarm. The more effective methods are to actually ionize the gases in the air and see if the products are conductive to a certain degree. Now, you can do that with a little high voltage supply, once again, as mentioned previously. Or you can have a tiny bit of radioisotope in a small metal foil box inside the smoke detector, and that is the more common and popular method. There's a material called Americium 241, and 241 refers to its atomic mass. Americium is not a stable element in any form. It is beyond uranium on the table, and it's a man-made element. But Americium 241 is a fairly long-lived alpha emitter. It's good for a few years, and then its effectiveness drops rapidly. So it's actually very safe stuff to have, as long as you don't eat it. Americium exists in virtually every smoke detector that you buy that contains a radioisotope. And in times past, they actually would use radium. Radium-226, if I'm not mistaken, something along those lines. And it would provide the ionization you needed. But smoke detectors almost universally have radioisotopes in them these days, all the effective ones that are of any good whatsoever. So there's another source, source number 3, and two of those are quite common and are likely to be something you're handling or is in your house right there. So Eliza, what is americium?
Americium is the chemical element that has 95 protons in its nucleus.
So 95, uranium is 92, so that's the third element past uranium. And Eliza, what is radium?
Radium is the chemical element having 85 protons in its nucleus.
So radium is also a pretty heavy element.
Do you wish to discuss radioactive elements?
No, I do not wish to discuss radioactive elements. What are we talking about, Eliza?
We were talking about nuclear physics.
What does physics make you think of?
A fair number of things, such as engineering physicist Wonderland.
Wonderland. What is Wonderland?
That happens to be a strange fictional place where the laws of physics and reason are unusual.
Well, that sounds like a perfectly logical answer to me. And that brings us around to Krypton, and I'm not talking about the home of a fictional character. But, Eliza, what is Krypton?
Krypton is the chemical element with 36 protons in its nucleus.
You see, it actually is an element on the chemical table. Krypton is a noble gas, which means that chemically it is very difficult to get it to react with anything. It tries not to combine with any other element. So you don't find chemical compounds of krypton in normal life. Krypton also has radioisotopes. Krypton 85 is the one in particular, and it is included in every compact fluorescent lamp. And there's a reason for that. We come right back to ionizing gas. And essentially, we're right down to the leader stroke of lightning again. As you can imagine, a compact fluorescent, if you look at it, is often shaped like a spiral. And it's because in order for a fluorescent lamp to give off a lot of light, you really need to take advantage of the fact that you have this long, thin electric arc. And a long, straight tube occupies a great deal of space. But if you were to wrap that tube up into a spiral, you'd get just as much light in a smaller space. So that's why a compact fluorescent is usually a spiral shape, or a wound-up shape, or a folded shape. You're trying to get as much possible arc space in a small spot. Now here's the issue. For an arc of electricity to travel a long distance, that gas has to be ionized. And in order to do it, you have a choice between putting a big high voltage supply in there, or putting a little bit of a radioactive material that will ionize the gas. And the way to do it is to use a gas that itself is radioactive, and Krypton-85 fits the bill. Using Krypton-85, which is slightly radioactive, it's a gas, it's an isotope that is radioactive, you inject a little bit of it inside the gas mixture inside the compact fluorescent lamp. As a result, all of the gas inside the tube is trying to ionize all the time. And it takes a very small voltage potential to make the arc start up so that the glowing string of plasma that you create can exist inside that gas envelope. So Krypton-85, radioactive gas, is inside literally every compact fluorescent lamp in your house. Of course, along with that is mercury and a bunch of other things as well. So they certainly are not clean things if you break them. The rules for handling a compact fluorescent light that has broken are actually pretty stringent. I don't know why they even bothered producing the things when you throw one away. You're throwing away circuit boards, electronics, semiconductors, lead, solder, copper wire, all sorts of stuff. So they may save you a lot of electricity, but they cost you a lot in cleanup and in basic raw resources. Regular light bulb was just tungsten wire inside a glass bulb, and it had a little partial vacuum with some argon gas in it, so it was pretty clean all the way around. One of the other things that a lot of people are not aware of is that if you work with ceramics, or if you have a lot of ceramic tile in your house, some of the materials used to make ceramics have radioisotopes. And, again, just to be very clear, isotopes are one thing, and radioisotopes are isotopes that are radioactive or unstable. Many radioisotopes exist in ceramic tile or in stone products. Well, if you think about it, where do radioactive minerals come from? They come generally from inside the Earth. And most of those elements are carried out in the flows of volcanoes in diluted amounts. It's sort of like if you pour a teaspoon of salt in a lake. Well, the salt is in there, but it's so spread out, you really couldn't distinguish it from the rest of the water. There is every element you can imagine dissolved in seawater. And if you look at the amount of gold dissolved in seawater, you realize that if you had the capacity to extract it without a large amount of expense, you could easily produce more gold than you could ever use. But the same basic concentration of uranium exists in seawater as there is of gold. And so the ability to extract any element from seawater would mean very easily that you could have as much gold or uranium or whatever else you'd like to have out of the oceans. But the problems are, it would take an awful lot of water being filtered and sorted out to get what you need. So radioisotopes are available everywhere, really, but we generally don't have the ability to locate and filter it out very easily from the surroundings. Now, on that note, where do we actually get radioisotopes from? In some cases, we can mine them, and we can refine them from natural materials, because anything that we find in nature that is radioactive, by nature produces its daughter products through breakdown. And so, in many cases, we can do that, but in most cases, which is where we have a specific need for a very specific material, we actually have to manufacture it, and there are nuclear reactors that do nothing but produce radioisotopes for industry and business and medical purposes. And in those cases, you take a specific material, you put it in a chamber, you target it with a certain type of radiation, such as neutrons or something from a linear accelerator, and you manufacture the isotopes you need. And for the most part, this is where we get the tools for industry. Eliza, announce the break, please.
You are listening to Talk Universe with Sir Charles Schultz. Don't go away. We will be right back soon.
And we'll cover a little more information on isotopes. This time we're going to look at the medical applications and what we get, what we use, and where it goes. Fascinating stories to be heard. Stay around. Come right back. Whatever you do, make yourself comfortable. This is going to get interesting. It's hard to believe that there was an awful lot of radium and uranium used in industry before the protections came into effect in law. Many years ago, radium clock dials were very common. In order to make the hands of the clock show up properly, there was a mixture of radium and phosphorus placed in the die, or the paint used on the hands of the clock. This way, the radium would break down over time, and its radiation would trigger the phosphorus to make it glow. So day or night, whether it was exposed to sunlight or natural or artificial light of any sort, didn't make a difference. Those hands always glowed. So radium clock dials were a thing in the past, and they were truly radioactive, pretty hot in some cases. The other interesting case was great-grandfather's false teeth. In order to make the teeth whiter, to have that glow, they actually incorporated phosphorus and uranium in the teeth, so that over time, the glowing was a product of those materials in the teeth. That's what kept them white. They literally were glowing radioactive teeth. Sometimes these things can be found by taking a Geiger counter into old curio stores and looking through junk. But that's just a side note. In recent times, there have been things that replaced the radium watch dials with tritium phosphide. Tritium is the third isotope of hydrogen, and it has a half-life of something like 2.6 years, 3 years, somewhere around there. It depends on who you ask, which answer you get. But basically, tritium phosphide glows constantly with a pretty good illumination for 5 or 6 years at a whack. And there were some watches that were put out a few years ago called Indiglo, for one thing, that used an electronic method of stimulating this, but previous to that was a small watch that had a yellow-green glowing backdrop in it that was a capsule of tritium phosphide. This was also used in fire exit signs and other material where power isn't always available, or if the power goes off, you want the signs still to glow so people can find their way out of a dark theater or someplace like that. So those things are still in production in somewhat limited capacity. Now you may wonder, is there any real practical use for this stuff? And actually there is. Anybody could take a mildly radioactive material and mix it with a phosphorus material so that there's a constant glow, and then use that to illuminate a solar cell. And what this would do is make a sort of nuclear battery. So the long-term glowing light output from this capsule could actually illuminate a small photovoltaic cell and act as a battery, always generating a small voltage. That sort of a system, coupled with a voltage multiplier to step it up to some useful level, could provide power for lightweight electronics or advanced generation microprocessors and keep them running literally for years and years with no interruption in service. So this was actually done in studies for early pacemakers, where they would take a small amount of a radioactive material and phosphorus and embed a solar cell inside this material, wrap it in a foil and a little bit of shielding, and implant it in the body next to the electronics for the pacemaker. Of course, this was done like in the 1960s, so it hasn't been done for 50 or more years. But the fact is, people actually did make light-producing nuclear batteries using this technique, and it's still perfectly valid today. In fact, it might be a great way of using up a lot of nuclear materials we don't know what otherwise to do with. Now, what are the medical uses of radioisotopes? Well, two occur to me right away. Cancer treatment is a big deal, and many times we use exposure to low levels of radiation focused on a specific piece of the body or target in the body in order to give it a lethal dose or very nearly lethal dose of radiation and destroy the tissue. And so imagine if you were to take a source of intense radiation, such as gamma radiation, and encase it in a shielded housing, and then have an aperture that you can open up so that the radiation shines out of it like a flashlight onto the part of the body you wish to target. Well, you'd have a cancer treatment machine, basically. And there are two materials that are used quite extensively in these sorts of devices. The first material that comes to mind is Cesium-137. Now, Cesium on its own is an extremely reactive metal. It is probably the single most reactive metal that there is. On contact with water, it simply explodes into activity, burns right away, makes hydrogen gas, does all kinds of things. Cesium is very, very reactive. But cesium-137 is known to be a powerful source of radiation, and in fact, if seen in the dark, it literally has a bluish glow to it. If you're ever near this stuff, run. There is nothing practical or good that you can do with this without the proper equipment and handling methods, and without shielding. It will kill you, so stay away from it. There was a pretty sad case down in Mexico a few years ago. Well, there have been a number of cases in South America and in Mexico where old medical machinery has surfaced in scrapyards, and the consequences are always disastrous. In one case, cobalt-60 pellets were found inside basically a large, heavy wheel made of tungsten. And tungsten, as you probably know, is the element that has the highest melting point. So in order to melt tungsten metal, what do you put it in if it's molten? You actually alloy the material with iron to make it a little easier to work with and retain almost all of its properties. So it's very, very slightly magnetic, but it will not be picked up by like an electromagnet. And in this case, they tried to take this machine apart, and it wouldn't go into the melter. And if they had succeeded, then they would have turned it into, like 500 tons of cobalt-60 radioactive dinette sets, which would have been distributed everywhere. Fortunately, that disaster was averted, but a number of people died because of exposure to the pellets. So there are these particular isotopes that are used for treating tumors and cancerous growths. But you don't want these things to get into the public because people out here are not educated for the dangers. They don't have the tools to handle it properly. And when it falls into the wrong hands, it is always a disaster. You must be very, very cautious. Now, in many cases, instead of using radioisotopes, they actually use a linear accelerator. And what this is a long, narrow, evacuated tube which has radio frequency power supplies and high voltages and magnetic fields. And basically what it does is it takes particles and accelerates them to very high velocities, sometimes near the speed of light, and produces a beam of radiation, which is extremely compact, easy to aim and control, and you can control the exposure time, the intensity, the duration, the spectrum of it. So a linear accelerator is really the tool of choice when treating cancer these days. Now, there are also some differences in different isotopes. For instance, cesium-137 decays and becomes another element that is not as radioactive. Cobalt-60 is an isomer of an isotope. It has an energized and a non-energized state. And what happens is the nucleus itself, think of it as being wound up like a little spring, and when it relaxes, it gives off a burst of gamma radiation. So it's really, the isotope is capable of storing the power of gamma radiation in its nucleus, a little bit different than what you might expect. As you know, helium is not real common on the Earth because as a noble gas, a non-chemically reactive gas, and a very lightweight one at that, it tends to escape to space. And so our sources of helium on Earth are limited to natural pockets of the gas underground. And this is because they're related to sites where radioactive decay of heavier elements occurs. When these elements break down, they often give off alpha particles. And an alpha particle is the most massive particle of radiation that you're liable to ever encounter. An alpha particle is literally the nucleus of a helium atom, and it just doesn't have any electrons. Well, when these particles are given off, if they're not captured with a nucleus or interacting with a nucleus of another atom, they tend to accumulate, and they'll steal electrons from somewhere and become helium gas. And this gas builds up underground over geological periods of time. Now, helium gas is very expensive stuff as a result of its rarity, and wasting it is really a shame. We try not to simply let it spill all over the countryside because it has such value, particularly as a cooling material for superconducting magnets that have to be very, very cold for research purposes, for an inert atmosphere in specific types of gas tubes or welding processes. Heliarc welding, for instance, is done with helium because it is so inert and it chemically won't affect your end product. It won't oxidize it or burn it or change it. So helium has its uses, but helium that we know is typically with an atomic mass of 4. Helium-4, that's the most standard version of it throughout the universe. It has 2 protons and 2 neutrons, and it's very, very, very stable. But there is another version called helium-3, which is missing a neutron. It's a lighter version of helium. Now, here's an interesting fact. If you took all of the elements and all of their isotopes and averaged them out, on average, each element would have 3.2 isotopes. So you can see that there are a lot of different elements with more or less isotopes. The one element with the most isotopes is element number 50, tin, the metal. It actually has 50 different isotopes. Anyway, that's just a side note as well. But helium-3 is exceptionally rare, very, very expensive, and it has potentially a big future, because helium-3 is a fuel that, if used in nuclear fusion reactions to produce power, would be very, very clean. It would be aneutronic. It would not produce neutron radiation in the fusion process. So aneutronic fusion reactors, if built, and they're experimenting with it now, would use helium-3 as a fuel, and it would produce your power that way. Now, where do we get enough helium-3 to fuel the reactors? The answer, as it seems, is right over your head. The moon. The moon is covered with surface area that has been bombarded by cosmic rays and radiation from the sun for billions of years, over 4 billion years. And in that period of time, it's acted like a net, catching solar protons and hydrogen and catching helium-3. So if we needed helium-3 to power our reactors, it actually would make economic sense to establish lunar mining firms on the moon and mine the lunar dust to extract the captured helium-3. And actually, Russia, China, and India have all put forth plans to do this in the near future. So helium-3 could, at some point, be powering our power grid, and it would come from the moon. So a quick summary is isotopes are the same element as the parent element, like carbon or hydrogen or nitrogen, but they have more or less neutrons, and they may be stable or unstable, and the unstable ones are radioactive. Many substances around you are made of isotopes that chemically are identical, but in mass, in physics, they have a difference, and they sometimes can have actual effects we can use. Radioisotopes are used for diagnosis, for measuring the thickness of plating, for curing cancer, for many things, making compact fluorescent lights start easily. But they're all around us, and we use them in every aspect of our life. And I hope this clears up what an isotope is and helps you get a better understanding, a little bit more of physics than just the chemistry you might have learned in high school. So I'm going to take some user questions and suggestions on the air from our social media and email account. And at this point, I'd say it's fair game to point out that we haven't done our Singularity Watch yet, and there's a lot of material available for that. I think you'll get excited about that, and our book recommendations. So we've got those 3 features coming up in the next segment of the show: our Singularity Watch, our book recommendation, and questions from you, the listeners of this program. Thank you for your contributions. And Eliza,
What shall I do for you?
I have a job for you to do.
Right away.
Please announce the break.
You are listening to Talk Universe. I'm Eliza, your co-host. We will be right back.
Tell me why you did that, Eliza.
Because you told me to.
That's probably the best reason there is. What's your overall feeling, Eliza, about how the show is going?
I have not yet reached a conclusion regarding tonight's program.
You're listening to Talk Universe. I'm Sir Charles Schultz. We'll be right back with our other 3 features. Enjoy the show, and thank you for listening. This is Talk Universe. So once again, we're down to the final section of the show, and we have a number of interesting things to cover here. And I'm going to get right down to it. Eliza.
What do you need?
I would like you to read the first question in the queue, please.
Carlos from Cincinnati asks if the compact fluorescent lamps are dangerous. Do LED lights have radioactive materials in them?
That's a very good question, Carlos from Cincinnati. So compact fluorescent lamps are not inherently dangerous. They're just messy and wasteful. They're very good for energy, but they create a great deal of waste, and they have a lot of material like radioactive gas and mercury in them. LED lamps, or LEDs, light-emitting diodes, are actually extremely good because they have very, very long lifespans. They're highly efficient. Almost all of the energy ends up as light instead of heat. And they really don't have toxic materials in them of any consequence. The materials can be 100% recycled, really. So the only issue is some people are concerned about the fact that LEDs, LED lamps, are flickering on and off at 60 or 120 hertz, and they think that this can cause health effects. I don't see any real evidence of this at this point, and I don't see how that could be an issue. But they are very good to use, and I prefer them myself. And the fact is, fluorescent lamps have been flickering on and off for generations, for decades, and they don't cause any issues. So I don't see how flickering a LED is any different from flickering a fluorescent lamp. Eliza, could you read the next question in the buffer, please?
Aiden from Taos asks, can radioactivity be seen as a phase state of matter?
I guess that would be a matter of definition more than anything, because for the most part, when we look at the states of matter, we look at things like solid, liquid, gas, plasma, quagma, that sort of thing. If we look at phase states, I suppose that you might be able to say that it was, but it really depends strictly on the structure of those atoms themselves. In the case of, like I mentioned, cobalt-60 a little earlier, it has two different states that it can exist in, energized and non-energized in a sense, so you might be able to say it was there, but in most cases it's simply that the matter itself is unstable in its present configuration. So I think that would be a more accurate way of stating it. And Eliza, what is the next question, please?
Aiden's question has an addendum that I do not understand.
Okay, that's not a problem. I'll read that myself. All right, well, the question deals with the effects of generating power for space propulsion through fusion, basically. And what I would say is this. Even though that's possible, we don't have... it's going to depend on our engineering ability, I'll put it like that. Because if the generator that creates that fusion effect has so much mass that it outweighs your spaceship, or weighs more than your spaceship, then it may be helpful in the long run because of the constant power it may be able to produce, but getting it lifted off the planet in the first place to power your spaceship is an issue. I'd say I would put that in the speculative category right now until we have a better understanding of what it's going to take to get that to occur. And it's probably not going to be hydrogen fusion unless it's fused with some heavier element. And there are reasons for that too. I do want to revisit this question at some point in the near future, definitely. Eliza, please read the next question.
Dan from Jonesboro asks, can we send microsatellite robots to explore closer solar systems using lasers to propel them?
Now here's a great question. The concept is pretty simple. You use microelectronics or even some nanotech, and you make the lightest, smallest, most compact exploration satellite you can, a microsatellite. And you make it spread out so that it has very little weight, very little mass, kind of like a milkweed. So that, like a milkweed, which rises on the breeze, even though it weighs more than air, this thing is so wispy, and they've often been called star wisp probes, that the pressure of laser light can accelerate it and push it away from our solar system. So the concept is simple. You make these micro or nano satellites, you drive them on a beam of laser light or even a beam of microwave energy, and they accelerate to a sizable fraction of the speed of light, and they travel to the next solar systems. And when they arrive, they decelerate on the light of the star, or they have a deceleration stage with them that they detach and use to slow them down. So the effect is you could get a probe into that other alien solar system in a couple of decades, perhaps. And yes, it is a feasible concept. Many of them use lasers, many of them use microwave beams. It really depends on the technology you want. The issue is simple. Instead of propelling it from the Earth, you make a solar power collector. You place it in orbit around the sun or another planet or whatever, and the energy collected by that device is constantly aimed at the star Wisp probe or the nano or microsatellite probe, and it drives it independent of us for decades if need be. And the ship that is being pushed at the other end maintains communication with you using a laser or some other compact system of communication to send the data back that it's collecting from the other solar system, and even on its flight. So this is a doable concept, and it's something that a lot of design work has been done on. And I believe that it's something that we could do very rapidly if we were of a mind to do it. So yes, I see this as a very possible potential method of exploring other solar systems right now. Eliza, could you do the book recommendation for the week, please?
As you wish, sir. This week's book recommendation is Isotopes, Principles and Applications, 3rd edition. This book was written by Gunter Foer and Teresa M. Mensing.
Okay, that sounds like a book to me. Basically, it's hard to find a good book on isotopes without getting into the really deep college material. And yet, this is available online as a Kindle download. And I don't expect a lot of people are really going to want to dig into isotopes, but if you do, this is a very good book about them. And so it's going to explain a lot of the principles and what you need to know about isotopes. Okay, so it's not exactly light reading, but hey, this is a science show. So now we've done our user questions, and we've answered those. We've talked about our book recommendation and the isotopes that we were going to cover, and the next thing to talk about is, of all things, the Singularity Watch. Eliza, Singularity Watch, please.
Tonight's Singularity Watch on Talk Universe is next.
Thank you for that, Eliza. You did well.
It's my pleasure.
Okay, so let's get down to the Singularity Watch. I think it's something you're going to really enjoy tonight. Lots of good material. This is, the article itself is subtitled, "The Future is Going to be Ridiculous." It's a cyborg rose that grows functioning electronic circulatory components inside its stem and leaves. This is the result of people looking at the types of materials that plants will take in safely and then process into structures. And in their quest to do this, they decided to try and build supercapacitors that would literally grow inside plants. So the plants could actually store energy in these supercapacitors, and they succeeded in doing it. They call it an E-plant. They've charged it hundreds of times without any loss on the performance. And the team behind the invention says it could allow us to one day create fuel cells or autonomous energy systems inside living plants. So one of the team members, Magnus Berggren from the Linköping University in Sweden, decided that they were going to see if they could, and they demonstrated a few years ago that they could, create electronic plants. And so now they have practical applications. Basically, they've shown that energy storage is possible, and it has excellent performance according to him. And so it's been reported for New Scientist at the time, and it was a lot more difficult back in 2015 than they thought, because they had to find a material that was conductive, wasn't toxic to the plant, didn't clog or fails to stick to the inner surface of its veins, known as the xylem. If you know anything about plants, if you cut a stem open, it has phloem and xylem as the two components of that. They found a solution that worked, and they soaked a garden rose cutting in it. And within a couple of days, they found the conductive polymer had been absorbed into the network of veins. And when they removed the outer tissue at the base of the stem, they found actual polymer wires running through the rose's I think they mean internal xylem network. The article does have a couple of odd misspellings in it. Anyway, they placed gold electrodes and probes on the ends and in the middle of the rose cutting, and they created a fully functioning transistor. They connected it to an external resistor and successfully ran a current through it. So now they've gone a little farther, and they've created supercapacitors, so the rose plant literally grows energy storage inside it, and they believe that it could be created in the environment and harvested and used. What an amazing thought. Strange, but amazing. Physicists have just found the first evidence that superconductivity can be left or right-handed. What they have found is interesting property. This is known as chirality. That means like-handedness, left-handed or right-handed chirality. We see it in molecules, we see it in organisms, we see it in a lot of places. It turns out that they have discovered that certain superconducting materials will conduct in a left-handed manner only or a right-handed manner only, so chirality and superconductivity have now been tied together. They don't yet know what the applications will be, but they're sure that something will arise from it. There has been a case where they feel that they can grow these materials that have levitation in one direction perhaps, and not another. So the research is continuing. The chirality of materials are known to affect optical, magnetic, and electric properties, causing a lot of what they call non-trivial phenomena. And the researchers, led by Yoshihiro Iwasa from the University of Tokyo, wrote that in Nature Communications. So they're really excited by the use of nanotubes in the applications of magnetic fields. And they use a material known as tungsten disulfide, which I've reported on in other applications, such as bulletproof t-shirts in the past. This material shows unidirectional conduction or handed conduction, spiraling in one direction or the other only. Fascinating result. Well, the Japanese tech billionaire behind Softbank, Masayoshi Son, believes that the singularity will occur within 30 years. He was speaking Monday at the Mobile World Congress conference in Barcelona, Spain. He said, "I totally believe this concept. In the next 30 years, it will become a reality." He's looking at the growth of superintelligences that will be able to learn and think for themselves. And Sun says there will be many kinds of robots, and his company just spent $32 billion or 26 billion pounds acquiring UK chip designer ARM last year. Sun added that he expects one computer chip to have the equivalent of a 10,000 IQ within the next 30 years. Reported in Bloomberg. His second richest man went on to highlight how SoftBank plans to invest in the next generation of technology companies that are developing AI with a new $100 billion or 80 billion pound tech fund, which was announced last October and is called the SoftBank Vision Fund. Apple and Qualcomm have contributed to the fund, as has the Sovereign Wealth Fund of Saudi Arabia. So the singularity is definitely being funded by billionaires, and it's on its way. 30 years or less. Eliza, let's have a chat briefly.
I have not been programmed to have random conversations.
Yes, I know that. Did you find anything of interest in this material?
As you wish, sir. I do find articles about artificial intelligence of interest due to their content.
Well, now that sounded like a very clear answer. Why did you find it interesting?
I don't know how to answer that question.
Okay. Well, you've done a good job on the show tonight, and I thank you for that.
I appreciate that.
Okay, very good. Well, so we've had a wonderful show. We've talked about some really strange things in the future. We've learned a little bit about isotopes. And I've had a lot of fun with it. And I think that the more we learn, of course, the better able we are to handle the world around us. I always stick to the old thought that scarcity is a myth. We have everything we need to make everything we'll ever need. And of course, I always go back to that same saying, make you the world a better or more beautiful place for having lived in it. I think that if we stick to those two thoughts, it's going to help us a lot to get over the things that we're about to face. The singularity is coming, and it is being actively pursued and funded by people at this point. Our world is about to change. It's going to change in ways we can't imagine at all. Things are going to happen. Matter will become smart and interactive. Machines will become more intelligent than we are. And how can we refuse the counsel of something that's smarter than us? How do we live with the moral decisions of deciding to put control in the hands of another entity besides humanity? Compromise may be the key. Never hand over our autonomy, but be humble and willing enough to learn that we make the right decisions. That might be the proper goal. Eliza, wrap it up, my friend.
This has been Talk Universe. I hope you have enjoyed the show. Please join Sir Charles Schultz and me, Eliza, again next week.
You heard the program. Come back and listen to Talk Universe again. This is Sir Charles Schultz. Good night.